All right, so on Earth, gravity is a force that always acts which way? Downwards. Which way is downwards? It's actually the way that gravity acts. That's how we define downwards. It's the way gravity's acting. If we happen to live in an area where there's a bigger mass over to the side here, and if you hang a string and it points slightly that way, that's the way we call down. Down is the way gravity points. Okay? So on Earth, that usually is approximately towards its center, but not always and not exactly. There are areas where there are larger densities of rock. So over in the Pacific Ocean, so sorry, that's the Atlantic Ocean there, but on the other side of the Pacific Ocean, there's a region where there's a very large chunk of very heavy, more dense material under the ocean, and it causes the ocean to pile up in that area. So sea level is actually about 200 feet higher in that area. So as you're sailing along in your boat, you're actually going uphill, sort of, because there's an extra pile of water piled up in one area because there's stronger gravity pulling it together there. And of course the gravity of the moon affects how high the water is. That's why we get tides, right? So that's gravity. And the way we find the force of gravity on Earth was m times g. You guys remember that? mg is the force of gravity. If mass is kilograms, g is 9.81 meters per second squared. The force of gravity is in meters. Okay. So the ancients believed that the world worked like this. The Earth was the center, and then we had water above the Earth, and then we had air, and then we had fire. There were four elements: earth, water, air, fire. And they all had their proper place. The proper place of Earth was on the Earth. The proper place of water was above the Earth. The proper place of air was above the water. So if you took a bubble of air and you hold it underneath the water and you let it go, what did it do? It went upward because that's its proper place, right? If you have a rock and you let it go, where does it go? Down. Why does it go down? Because it's going to its proper place, right? That's the idea. The proper place for fire is above the air, and so when you burn a fire, the sparks fly up. The sun is fire, so it's above the air, right? Why does a log float? How do you explain that one? If you're Aristotle or Ptolemy. A log, why does it float? Yeah, it's a mixture of earth and air. And so the mixture of the air in it keeps it above the water, right? So that's how they explain their world. They didn't ask why do things fall. They just fell because that's where they went. That they belonged there. God made the center of the universe the earth, and all the earth should go to the center, down. Okay? So that began to fall apart, and we'll talk about how that fell apart later. But we're just going to jump ahead to Newton. So Newton's sitting under a tree and an apple falls on his head. Probably not true. It's a myth. But he does consider gravity, and he understood that an apple that is falling is actually accelerating. So the only thing that causes acceleration is their forces. So there must be a force acting on the apple, and he called it the force of heaviness, or in Latin the word for heaviness is gravitas. And so he called it the force of gravity. So he was the first one who clearly recognized that an apple fell not because it was going to its proper place, but because there was a force acting on it, and the force acting on it came from an interaction with the earth. Okay? So he sort of ran with that a little bit. You guys did a lab yesterday. I don't know if you noticed those numbers you were using, those forces. They were like 10 to the minus 8 newtons. We're talking billionths of a newton. That's why we can't do it in class. We can't take 2 jugs of water and measure the force of gravity between them. It's astronomically small, the force of gravity, between 2 normally sized objects. So we had to do a simulation, but what you guys found was the same thing that Newton sort of figured out from the thought experiment. Okay, so Newton deduced that if you had an apple that was twice as massive, the force of gravity must be twice as big on it, right? So that leads him to think that the force of gravity is proportional to masses. Making the mass bigger makes the force of gravity bigger. He couldn't change the mass of the earth, but he could change the mass of the apple, or whatever it is he's thinking about. Okay? He also reasoned that the force of gravity must be diluted by distance. So this is a really important idea. So let me just kind of work on it for a minute. Imagine a light bulb shining and the light spreads out, right? If I were to put a piece of paper here, the paper would be illuminated by a certain amount of light. If I move twice as far away, whatever light would have hit one page is now spread out over 4 pages. It is diluted, right? The same amount of light hits this page or those 4 pages. So making the distance 2 times bigger makes the illumination 4 times smaller. Does that make sense? If I were to go from 1 meter to 3 meters, what would have hit one page is now spread out over 9 pages. So this idea of diluted by distance, which Newton was after, is really what we call an inverse square law. The illumination is inversely proportional to the radius. As the radius gets bigger, the illumination, the brightness on a given page, gets smaller. That's inversely. But going twice as far away doesn't make it half as bright. It makes it a quarter as bright. Going 3 times farther away makes it 1/9 as bright. Okay? So anytime something is diluted by distance, it spreads out. This could be a paintball bomb. This could be a sound source spreading out. So if you are twice as far from me, the intensity of the sound is 4 times smaller because sound spreads out in all directions. So it's diluted by distance. Anytime something is spreading out spherically in all directions, it falls off, it gets smaller by this 1/r² relationship, okay? So Newton assumed that gravity must somehow act the same kind of way, all right? Wasn't really sure, but he ran with it. So what happens? So he assumed it's an inverse square law. He deduced it's proportional to the product of the masses. He couldn't change the mass of the Earth, but he could change the mass of the apple, so that kind of led him to that. You put all that together, and you get the same thing we got in lab, which is that the force was directly proportional to mass too, right? And guys, when you write math models, write equations. It's y, the force, equals the slope times what's on the x-axis plus the intercept. There's no intercept, so you can leave that off. And here you graphed 1/the distance in meters squared. So when you did that, you got a straight line. So you found that the distance, the force, was inversely proportional to the distance squared. And your math model looked like this. Okay? So that's what you guys found in lab yesterday. And that agrees with what Newton did. So here's what you end up with. So if you have your toolbox, your AP reference sheet, you might want to just locate this on there. This is the universal law of gravity. It tells you how to find the force of gravity anywhere in the universe. Okay? And this is in the table of constants on the front page. And the equation is in the list there on the back page. Okay? So one thing to note, this G is a universal constant, and it's tiny. It's 6.67 times 10 to the negative 11, okay? We're going to use that a lot this unit. So just for fun, grab your calculator, type 6.67 e negative 11, and store it in G. You guys don't use your storage facilities on your calculators very much. Just store it in G. Then you don't have to remember what the heck it is. And then you can just use G when you do a calculation. You don't need to type in 6.67 e to the negative 11. Also note the units on this thing. It's Newton, meters squared per kilogram squared. So when you solve problems, your forces are going to be in newtons, your distances are in meters, your masses are in kilograms. If you want to do it in feet instead of meters, you got to go find yourself a different value of G. This is the one you're going to get on the AP exam though. All right? Okay. So, how does the force of gravity depend on M1? By looking at this equation, what would you say? How does the force of gravity depend on M1?
Directly.
It is directly proportional. Which means, if M1 were to double, what happens to the force of gravity? It would double. Does that make sense? If the mass 1 were to get 7.5 times bigger, what would happen to the force of gravity? 7.5 times bigger. Okay? So that's pretty easy, right? How does the force of gravity depend on R, though?
Inverse.
No,
What?
it's not inversely proportional. It's inversely proportional to R squared. It's an inverse square law. So, what happens if R were to double? What would happen to F?
1, 4.
It'd be 4 times smaller. Does that make sense? So, that's what it means to be an inverse square law. What would happen if to the force, if the distance between them gets 3 times smaller? The distance gets 3 times smaller, the force would get 9 times bigger. Right? Does that make sense?
Yes.
So, how does the force depend on the radius? It's inversely proportional to the radius squared, right? Now, what's not obvious is how does the radius depend on the force? The force is proportional to 1 over r squared. But how does the radius depend on the force? If you were to rearrange this to get r by itself, what would you have? You would have f times r squared is proportional to 1. Divide both sides by f, and you get r is proportional to 1 over the square root of f. Right? So if you wanted the force to double, what would you have to do to the radius? If you wanted this number to be 2 times bigger, this would become the square root of 2 times smaller. Right? Does that make sense? If you want to double the force, if you want the force to be 2 times bigger, you got to make the distance between them the square root of 2 times smaller. Alright? I got some questions for you to practice that a little later. Alright, a key note here is that this distance is the distance between their centers. It is a really fun exercise in 3-dimensional calculus to prove it, but if you have an object right here, like an Earth, and you have another object right here like you, the force of gravity is actually, there's a chunk of Earth right here, and you're attracted to that this way. There's a chunk of Earth right here, and you're attracted to it that way. And this one over here is farther away. There's a force on you. There's a force on you going towards every single chunk of the Earth. And if you add up all those forces, it turns out that you get the exact same answer as if you were here and all of the mass of the Earth was located at its center. Okay? You can treat the mass of the Earth as if it's located at its center for finding the force of gravity. Even though it's not. It's spread out. And the forces are going in all kinds of directions, right? I'm being pulled downwards by Earth here, but there's a whole bunch of Earth over there that's pulling me this way. And there's a whole bunch of Earth over there pulling me that way. But the parts going in the horizontal direction cancel. And the parts going down all add up and give you the same answer. Okay? So, you can pretend like masses are point masses, and then the distance between them is between their centers. That really only works for spherically distributed masses. But most planets and things we work with are roughly spherically distributed, and you aren't really big enough to matter that you're not spherically distributed. Okay? So even though you're not very rotund, we can just pretend like all your mass is located somewhere near your belly button. All right. So, how do we find the force of gravity? Well, you just crank it out. Take G, which stays in your calculator, times M1 times M2 divided by R squared, and I'm going to assume you guys can all get that and keep moving. Okay, because this is a review of last year, I think, except for Lily. All right, a thing to notice there is that is 63 billionths of a Newton. You're not walking along and you pass Bradley and you're like, oh, I'm getting pulled that way, right? 63 billionths of a Newton you're not going to notice it. All right. One of the objects has got to be extraordinarily large. What is the really, really large object in your local neighborhood? The Earth. The Earth. So we feel gravity due to the Earth. We don't really feel gravity due to anything else. Okay. All right. Skip that. Okay, here I got Sally. I want to know, what is the force of Sally on the earth? Okay, you guys just wish you could have cool hair like her. How do you find the force of gravity between the earth and Sally? What do you need to know? What do you think? Ben? You need the distance between what? Yeah, the middle of the earth and the middle of Sally, right? So do you need to know how tall Sally is? No? How small has it got to be to not matter? What if Sally was in the top of a skyscraper? Does that matter? It would. If this is the radius of the Earth, 6,378,000 meters, where is the uncertainty in that measurement? Using our rules of significant figures. We always write down everything we know, and the last non-zero digit is our uncertainty, right? So where's the uncertainty there? In what? Ben?
Thousands.
What?
Is that thousands?
Yeah, the uncertainty is in the 8. Could be a 9, might be a 7. Which means we are uncertain by plus or minus 1,000 meters. Half a mile. Does it matter if Sally is 4 feet tall or 6 feet tall? The distance between her feet and her belly button is insignificant compared to the uncertainty of the radius of the Earth. So the short story is that as long as you are within a half a mile or so of the surface of the Earth, you don't have to worry about how tall you are, whether you're on the second or third floor of the building. To calculate the force of gravity, we're just going to use the radius of the Earth. Okay? So we plug this in. We have the radius of the Earth. We don't care about how tall Sally is because she's not half a mile tall. We plug in the numbers and we crank out the solution. Go ahead and do it really quickly in your calculator just for fun. Take G, which you've already stored, multiply it by the mass of the Earth, which you might want to save also in capital M. I mean, you need to go to finish your contact. Multiply it by the mass of Sally, which is 50, and then divide by the radius of the Earth, which you might want to store in R, because we're going to use those all very often. So I would store them. That's what I would store for the rest of the unit. Make your life easy. But you don't have to, you can keep typing them in. Then you'll make a typo and you'll get it wrong. You'll try it 8 more times. Half an hour later, you'll realize you had a typo. You finally get the green check mark. Okay. Did you crank that in there? What'd you get, Sarah? Yeah, you get 490 newtons. Okay? Alright, now. Are we good? What would change about this problem, guys, if instead of Sally we had Bob? Because Bob has a mass of 75 kilograms. What would change? Would this change? No. How about that? No. How about that? Bob's a little taller. Does it matter? Nope. The only thing that changes is that, right? So when we try to find the force of objects that are on the surface of the Earth, or within half a mile of the surface of the Earth, it makes sense to go ahead and calculate what this mesh right here is. That mesh right there never changes as long as you're on the Earth, right? The only thing that changes is your little m. So go ahead, if you stored it, take G times m divided by r squared. Let's go ahead and pre-compute that mesh right there. And see what we need to multiply the mass by in order to get the force. What? Did you get 9.81? Holy smokes, where did that number come from? That's where it came from. That's why we call it. Now, what do we call this, guys?
Force of gravity.
What letter do we use? No. Little g, right? This is the local gravity constant right here in our little local neighborhood called Earth. So as long as you are on Earth, you can find the force of gravity by taking mass times little g. So what is little g? Little g, the acceleration due to gravity on our planet, as long as you're near the surface, is found by taking g times the mass of the planet divided by the radius squared. Okay? So, big G is the universal gravitational constant. It works everywhere in the universe. That's why it's big G. Little g only works here. So, it's just a little g. It's not so important. The people on Mars just don't care about our little g. Right? So, if you want to calculate the local gravitational constant, all you got to do is take big G, which never changes, multiply it by the mass of the planet, and divide it by the radius of the planet squared. So you end up with this. And this is not on the AP exam reference sheet. You have to know it. You have to know that little g is, so if the equation is the force of gravity anywhere is g, mass of object 1, mass of object 2 divided by the radius squared, you got to know that that part right there is what we call little g for a planet. Okay? And then if that's true, then the force of gravity on the planet is just m times g. Okay? So that is not on your AP reference sheet, but you'll get asked a question or two about it. Okay? Specifically, things like, what happens if the planet has the same mass as Earth, but twice the radius? So what would G be on a planet that has the same mass of Earth, same amount of matter, but twice the radius?
4 times smaller.
If you make R 2 times bigger, then G would get 4 times smaller. So instead of being 9.81, what would it be?
2.45.
What?
2.45.
2.45. That's it. That's G on a planet that had the same mass as Earth, but twice the radius. Okay? A word about nomenclature, how we use the words. If we have a satellite going around the Earth, the radius of orbit is the distance between the center of the satellite and the center of the Earth. That's called the radius of orbit, and we use R for that. The radius of the Earth is the radius of the Earth, and if I tell you h, or I tell you the altitude, I'm telling you how high above the Earth it is. So if the altitude of a satellite is 300 miles, you have to use the 300 miles from here to here, plus the radius of the Earth to find the distance between their centers to find the force of gravity. Okay? So when it tells you something is at an altitude, that's not telling you how far it is between the center of the Earth and the object. It's telling you how far it is above the Earth. Okay? The space station, the altitude is 300 miles. That's it. The space station, when it goes over our head, is closer than St. Louis. It's not very far up there. All right, an exam problem on the AP. So they're going to throw a slight twist at you on occasion. So I just want to make sure everybody's good on this. Density is mass over volume, right? You guys remember this from chemistry, maybe?
The row.
The letter is rho, but who cares? If the density is mass over the volume, then the mass is the density times the volume, right? Good so far? Okay. The volume of a sphere is 4/3 pi r cubed. You good there? So, if I were to double the radius of a sphere, what would happen to its volume? If I double the radius, what happens to its volume? If you make this right here 2 times bigger, what's 2 cubed? It's 8, right? So if you double the radius, what happens to the volume? 8 times bigger. If the volume gets 8 times bigger and the density is the same, what happens to the mass? If you have the same density, this doesn't change, but the volume gets 8 times bigger, what happens to the mass? It gets 8 times bigger. Okay? So here's the question on the AP exam a couple years ago that stumped everybody. A planet has the same density as Earth, but twice the radius. What is the acceleration due to gravity on this planet? So let's think through it. If it has the same density of Earth, and it has twice the radius, what will be its mass? So if you have twice the radius, what happens to the volume? 8 times bigger, right? If the volume is 8 times bigger, it has the same density, what happens to the mass? 8 times bigger. So, the gravitational acceleration on this planet, so planet X, will be g times the mass of planet X divided by the radius of planet X squared. Okay? What is the mass of planet X? It's 8 times the mass of Earth. You follow? So, the g, the mass of planet X is 8 times the mass of Earth. What is the radius of planet X? It's 2 times the radius of Earth. And of course that's squared. So, we've got an 8 in the numerator, we've got a 2 squared in the denominator, which is a 4, right? So I'm pulling out the coefficients. What is 8 over 4? 2. What is g, mass of Earth, divided by the radius of Earth squared? 2g. That right there is 9.81. Right? G times the mass of Earth divided by the radius of Earth squared is our 9.81. So for this new planet, its gravity acceleration, little g, is going to be 2 times that of Earth. So it's going to be 2g, or 19.6. You see how we get that? So that stumped everybody, they were all crying foul, but it wasn't really that hard of a problem, right? So if it has the same density of Earth, then if the radius is twice as big, the volume is 8 times as big, which makes the mass 8 times as big. Okay? So when you're solving problems like this, you don't have to actually calculate its density and multiply it out and work out the whole problem. You can just kind of use relationships like this. Okay? All right. A couple of notes to wind us up. Newton proposed an empirical explanation for gravity. So that means that when he explained, kind of gave you the right numbers, Newton had no clue how gravity worked. Not a clue. Nobody really knew how gravity. How does the Earth reach out there and pull on the moon? How does that work? Well, Einstein proposed a mechanism for gravity, and he proposed that mass actually warps the fabric of space and time. And it's the warpage of this fabric of space that causes a gradient potential, a force on it. Okay? So I'll show you a demonstration later when we do circular motion of that. He proposed this in 1905. It was called general relativity. And it wasn't until 2018, so 3 years ago, 3 guys from the University of Washington won the Nobel Prize for actually finally measuring these ripples in the gravitational space-time. It was the LIGO detectors they built down in Louisiana and in Washington State. They were able to measure the gravitational ripples from a black hole colliding. That was in 2016, and they got the Nobel Prize in 2018. So, Newton, 1666, proposed gravity. Einstein, in 1905, gives a mechanism for how it might actually work, and it's not confirmed until 3 years ago. Okay? So, pretty recent stuff going on there in the field of gravity. All right, you've got some problems to solve. It's a bit of a, there's quite a few. The first couple are conceptual, which mean they're just about relationships. You don't need to show any work. So go ahead and try to do those before you leave in 10 minutes. I don't want you to get stuck and frustrated on those. And then you've got some problems to solve. I don't see you tomorrow. Thursday we're doing a lab, a computational lab. And Friday we're doing a lab. So we're going to get more problems on Monday. So that's kind of your time frame. Okay?
How about that 3.1 links to lab 3.1?
Oh, that's a problem. Okay, let me stop this, Julia.